The three most important design considerations for energy efficiency. As much as we talk about energy efficiency in architecture, we often miss some important context. And before prioritizing specific design considerations, that's where I'd like to start. As it turns out, the government does a sort of census, but for buildings. The commercial building version is called CBEX, or the Commercial Buildings Energy Consumption Survey. And when we look at the data from these surveys, this is what we see. This graph shows the energy use intensity, how much energy we use per square foot for commercial buildings since the 90s. This is for all commercial buildings. It's not correcting for occupancy type or when or where the buildings were constructed. It's just an average to get a big picture sense of where we are in terms of energy use per square foot. And the data does not look very encouraging. The average commercial building in 1992 used 81 kBTUs per square foot, and in 2012, the average commercial building used 82 kBTUs. 2012, by the way, is the most recent year we have data. The 2018 data is set to be released later in 2022. In any case, this data does not make our industry look particularly impressive. And note, by the way, that this is energy use per square foot. Over this same period, the number of commercial buildings has increased, and those buildings are, on average, larger. In 1992, we had almost 70 billion square feet of commercial space, and in 2012, we were up to almost 90 billion square feet. So the consequences of our lack of progress is underrepresented by this chart. Things look pretty different, however, when we look at residential buildings. Our residential buildings, all residential buildings from single-family homes to apartments, used on average 55 kBTUs per square foot in 1993, but by 2015, the average residential building used 38 kBTUs per square foot. So it's pretty nice. That said, the average home is larger now, and it's possible that dividing energy use by square foot could distort the numbers and only make it look like we've made progress when we really haven't. We don't have quite enough information yet. When we look at energy use per household, we see similarly encouraging numbers though. In 1993, the average household used 104 million BTUs, and by 2015, that number was down to 77 million BTUs. The energy use per household member is down too. In 1993, the average person used 40 million BTUs at home and only 30 million BTUs at home in 2015. What this means is that our homes have been getting so much more efficient that we've been able to compensate for having larger homes and fewer people living in each home, which is astounding. But it also invites some interesting questions, such as, why are we seeing so much progress in our residential buildings and so little in our commercial buildings? This is an incredibly interesting topic, especially when it comes to commercial buildings. And in this relatively short discussion, we're obviously not going to be able to explore this topic as thoroughly as we might wish. But we are going to be able to identify some important rules of thumb that really can and should help us prioritize among design decisions in day-to-day practice. We can separate this discussion of energy use into two categories: the way the building enclosure is designed and the way the building is operated. With respect to the enclosure, the three most important factors that influence how much energy our buildings use are: 1, glazing ratio, how much of the building is glass and how good is that glass. 2, airtightness, how airtight is the enclosure? How well have we separated the inside from the outside? And 3, insulation. How much insulation are we using and is it continuous? And these three factors are listed in order of importance. That's a bit surprising, isn't it? I think a lot of people, probably a lot of our clients, just sort of intuitively think that energy efficiency is mostly related to insulation. And that's true in a sense. Insulation is in the top 3. It's certainly important, but a building's glazing ratio and airtightness are more important. Understanding these three factors helps us understand a bit better why we've struggled to make improvements to our commercial buildings, doesn't it? In residential design, we don't have the same demand for all glass enclosures that we have in commercial construction. Similarly, it's pretty easy to pop a blower door on a house to get a sense of the airtightness of the enclosure. Now, we can do this in commercial architecture too, but we don't most of the time. It's more complicated. Our residential buildings also tend to be made out of non-conductive materials like wood, which makes achieving continuity in our thermal control quite a bit easier. Okay, so I'm telling you that glass matters a lot, and we tend not to use too much of it in residential construction. And after glass, air tightness and insulation are the next most important factors related to energy efficiency. So it's pretty reasonable to attribute our energy gains in residential construction to better glass, better air tightness standards, and the use of more insulation. But I don't think it's enough to just tell you this. I'd like to take you through a little thought experiment to better illustrate the relative importance of these three factors. Let's take a hypothetical wall. Suppose 50% is glazed and 50% is opaque. And suppose the wall portion is R20, and suppose the window portion is R2. For the purposes of this little thought experiment, don't think of this as a real wall with studs and thermal bridging and construction defects. Just think of some kind of monolithic R20 material perfectly joined to some kind of monolithic R2 material. What will the average R value of this facade be? Will it be A, about R11, B, about R4, or C, about R18? And we're going to go through this together, but here's some think time if you really want to guess. Okay, the equation we use to calculate the average R value of the facade is this. It's not a straight calculation of average, and the reason is outside the scope of this discussion. Anyway, if we use this equation on our hypothetical facade here, we end up with an overall R value of 3.6. So the answer is B, or about 4. And that's crazy, right? By making half of the facade glass, our overall thermal performance is 80% less than the performance of the opaque wall alone. Now, I know I said this wasn't a real wall, but I picked these numbers on purpose. A standard residential 2x6 wood wall has R21 cavity insulation, and R2 is the same as U0.5, which is pretty average for residential glass. It's also about what we see even in thermally broken commercial aluminum windows and curtain walls. Let's take this thought experiment a little further though. Suppose we were to double the performance of the wall to R40. And before we look at what effect that has on overall thermal performance, let's talk about what it takes to get a standard residential wall from about R20 to R40. We have to add exterior insulation, and not a small amount of exterior insulation. We have to add R20. So we're looking at 4 inches or more of exterior insulation. This has some pretty significant cost and design implications, but would it also have a significant effect on overall thermal performance? So let's see. It would bring our average R value from 3.6 to 3.8. That is a lot of work for barely a rounding error of added performance. You can play around with combinations more, which is kind of fun and surprising, and I encourage you to do that to kind of calibrate your intuition related to window to wall ratios and window performance. But I can tell you where you'll end up, and that is with a real appreciation for how much glazing matters. Glass is so much less thermally efficient than even the worst walls that it disproportionately influences overall performance. The very best glazing systems top out around R10 or so, and the humble residential 2x6 cavity insulated wall ends up being around R17 or R18 when we account for the thermal bridging of the studs. Before moving on, I'd like to combine glazing and insulation in a more realistic way that really puts this in context. I'm going to show you a graph showing the overall thermal performance of 3 residential walls, including the windows. Each wall has an 18% glazing ratio, so 18% of each of the walls is glass and 82% is opaque. The graph plots the overall effective R value for the wall, including the windows. That's on the vertical axis. And the overall performance of the walls is based on how good the windows are, which is on the horizontal axis. Each line represents a different wall. Again, all of them are 82% opaque and 18% glass. The top red line is an R30 opaque wall. The hot pink line is an R20 wall, and the light pink line is an R10 wall. What you'll notice is that at the right side of the graph, where the windows aren't very good, there's very little difference in the overall performance of the three different walls. So if you have crappy windows, whatever you do with the rest of the wall doesn't matter all that much. But as you move left and improve the glass, you'll notice that the difference in the walls becomes much more pronounced. An R30 wall performs much better than an R10 wall when the glass is better. And the relationship isn't linear, it's exponential. And that's really what I want to emphasize. This shouldn't be a reason to hate windows. This should be a reason to invest in windows, and not just in the actual performance of the windows that you purchase and install, but in the way in which glazing is incorporated into the design as a whole. We know that a lot of poorly designed houses are much larger than they need to be. A good architect can make a more modestly sized house more functional and more comfortable simply with careful and attentive design. The same is true of glazing. And by the way, even heavily glazed houses don't actually use that much glass when you actually calculate the glazing ratio. And I encourage you to do that, by the way, as a way of calibrating your intuition. My house, which we're filming in right now, has a glazing ratio of about 16%. It's a traditional craftsman style house, and it feels pretty bright and comfortable to me, even on a rainy day. Do some back of envelope calculations of some of your favorite spaces, and I bet you'll be surprised at the actual glazing ratio. So, bottom line, invest in your glass, then invest in airtightness, then insulation. But these are just enclosure-related factors influencing energy efficiency. In introducing this topic, I told you that there were two categories of factors influencing energy performance: design factors and operation factors. In residential design, interior conditions are optimized for comfort. In commercial buildings, they're optimized for productivity. This is a huge difference, and it's hugely influential. Residential construction has benefited from the positive feedback loop between comfort and energy efficiency, particularly with respect to that second most important design factor of airtightness. Airtight buildings are substantially and noticeably more comfortable for occupants. They're better at dust and allergen control, pest control, odor control, acoustic performance, and thermal control, including draftiness. In commercial buildings, the relationship between the owner and the occupants produces very different accountability structures, and we don't benefit from the same positive feedback loop in the same way. And the focus on productivity over comfort means that we also tend to ventilate commercial buildings at much higher rates than residential buildings. Depending on how you run the numbers, the ASHRAE recommended ventilation rates for each, residential and commercial, are roughly in line when we account for occupancy and square footage. But in practice, they're orders of magnitude apart, mainly because people don't actually operate their houses at the ASHRAE ventilation rates. This is a much more complicated and controversial topic that's hard to really simplify. What I'd like to leave you with is that the more air we bring inside our buildings, the higher the ventilation rate, the more energy we need to expend to condition that air, which isn't to say that we shouldn't do it, but ventilation is a lot like glass in that it's extremely important, and we would do well to invest in careful and considered design decisions. If you're interested in that topic in particular, I teach a course on ventilation for architects and builders. It's about 2 hours long and requires no special knowledge of ventilation systems. It's on residential systems, but the context and principles apply to all buildings. I hope you'll check it out.